Introduction to exercise 10.4 on the binomial distribution. We're going to look at, in particular, the Bernoulli sequence, which is pretty much the only sequence we're focusing on. It's a very simple definition of the Bernoulli sequence, and as long as you understand what it is and the conditions met, you're fine. We're going to look at, for example, the mean variance, etc., and also graphing what that looks like, and how to solve those more complicated scenarios like we were saying earlier. For example, what's the probability of getting 3 heads out of 15 coin tosses without having to do every single option or write out a tree diagram for the entire situation. And then at the end we'll look at the number of trials, how to calculate the number of trials. But this is a very calculator heavy topic, so just giving that heads up. It's most likely exam 2. A quick review of the combination and Pascal's triangles. I believe you would have done some sort of had some sort of connection last year regarding this, but a quick reminder: combinations or selections is a method of counting the number of ways in which objects from a set can be selected. The order of selection is ignored. For example, when selecting 2 letters from A, B, and C, there are 3 distinct selections: AB, AC, and BC. There is no AB/B. A being 2 different scenarios, right? Just a quick reminder. We'll go through a quick example. 4 flavors of ice cream: vanilla, chocolate, strawberry, and caramel are available at the school canteen. I wish. How many different double scoop selections are possible if 2 flavors must be used? A quick reminder. Of course, we have 4. There we go. 4 total options. And we also have 2 selected, I should say, rather than picked. Selected. We use this. Does that look familiar? Lovely. NCR, which in this case I'm going to rewrite as... Actually, no, I'm going to keep that there for now. NCR, in this case, we're going to replace N with... Apologies. We're going to replace N with 4 and R with 2. So we're selecting 2. That's an R. And then we're having a total of 4 options. So that's 4, which equals 2. And we're going to use the formula, which is right underneath here, which is then going to be 4 factorial over 2 factorial 4 minus 2 factorial, which equals 2. And I'm going to, yes, go for it. Combination. Yeah. Which I'll show you where it is in the calculator as a reminder later on as well. So we have 4 times 3 times 2 factorial, 2 factorial, 2 factorial. I'm just going through the long way to show you that you can simplify just by doing this, which gives an answer of 6, bless you. So a total of 6 possible combinations. Right, and that's a very basic example, it's just more so revision. The formula is below. You should most definitely have this written down or memorize it as well. In general, selecting R objects from N objects will have the following combination. In your calculator, I'm going to quickly open up my calculator as well. It is in some obscure spot, right? But you have to open up your keyboard. So if you go to your main screen and then open up your keyboard after your calculator loads. Here we go. Alright, so if you open up your calculator, go to your main screen, go keyboard. My keyboard's very small, apologize. You have to press the down arrow, right? The down arrow and then the advanced option. So just to repeat, you open up your keyboard, which is very small on my screen. You press the down arrow underneath ABC to show more options on your keyboard. You're going to select the advanced, and then on the very top right is your NCR, where your first value is N and your second value is R. So for example, if I type in 4, 2, it should give an answer of 6. Okay? So that's where your NCR is. This is closely linked to your Pascal's triangle. I'm just going to draw this down. You don't need, this is not necessarily mandated understanding, but it's more so just a contextual information. You can see how these are very closely linked, Pascal's triangle and your combinations. I'm expecting our factorial work to be good, so I'm not going to spend too much time on it. We're going to move on to our Bernoulli sequences. Next page. You know I love my conditions, so here is our condition, or here are our conditions for our Bernoulli sequence. 3 conditions. First one is that each event results in one of two outcomes. So basic example, coin flip, yeah, successful failure, that's it, right? It could be, for example, it could be saying, well, if I'm rolling a dice, it's 1 out of 6, right? Or 1, 2, 3, 4, 5. It's not one or the other. But it could be, well, getting an even number. That would be fail or success, right? So it's each event resulting in one of two outcomes. The second one is the probability of success being constant for all events. So, for example, if I flip a coin, right? If I flip a coin again, it's not going to change the outcome, right? And of course, each event being independent. So pretty straightforward. Understanding where we're going for is that they're independent events and that it's only successful failure. A binomial distribution is describing the probability distribution of a Bernoulli sequence of n trials with p probability of success. That is a variable that comes up quite often, so please make sure you log that into your memory. If x is the number of successes, this is the formula. The probability of where x equals to x, or in other words, the probability of where x equals to 3 or 4, whatever it is, right? So I'm going to go back to the chocolate chip scenario. The probability where there are 3 chocolate chips, or there are 4 chocolate chips here. You see how even though there are more options, it's more the probability that there are 4 chocolate chips, yes or no. So that becomes a Bernoulli sequence, equals to your nx, so that's your NCR from earlier, or NCX, multiplied by the probability of success to the power of x, multiplied by 1 minus your probability of success, so in other words, your probability of failure, to the power of n minus x. And a quick reminder of the formulas there, but you don't need to copy that one down. That's the same one from earlier. Okay, let's jump into an example. Find the probability of obtaining exactly 3 heads when a fair coin is tossed 7 times, correct to 4 decimal places. You can see how this would be very annoying to do by hand. Let x equal to the number of heads, and little x equal to 3 heads. I know that my probability is going to be equal to 0.5 because it says it's a fair coin, and n equals to 7 because that's how many total flips I'm doing. Now, a lot of students make the mistake of writing calculator syntax, and it's something I will hammer down closer to the exams, right? Please do not write what you put in the calculator for a couple of reasons. The first reason is examiners don't like it. The second reason is the ClassPad is not the only calculator being used, right? If the examiner doesn't use ClassPad, well, you're screwed, right? So write down a universal or conventional notation. I'm just writing in general terms here. X, and then you do your tilde, binomial, so BI, NP. So in our scenario, it would look like this. Oh, examiner, I'm writing into my calculator. I'm trying to find 7, 0.5. Okay, let's go ahead and solve that. So in other words, the probability of x being equal to 3, right? I'm going to write the formula down. Let's not do this one using the function yet. I'll show you the function in a moment, but let's pretend that we don't know it yet. So the probability of x being equal to 3 is 7, 3, right, combination, multiplied by 0.5, because it's a probability of success of 0.5 3 times, so to the power of 3, multiplied by 1 minus 0.5, which in this particular scenario you could just write 0.5, to the power of 7 minus 3. Putting that into the calculator, actually, you know how to put that in the calculator. I just tell the answer is approximately 0.2734. I'm going to move swiftly. There are quite a number of content bits to learn. The next question says the probability of a netballer scoring a goal is 0.3. Find the probability that out of 6 attempts the netball scores a goal. Well, this one's pretty straightforward. It's exactly the same. I'm just going to write the same understanding, where the probability of x being equal to 4. Now, in most scenarios, I would most definitely recommend you write let x equal to, etc. Right? But in this case, I'm lazy. But you understand you need to write x equals to, etc. So a combination x4 multiplied by 0.3 to the power of 4 times by 1 minus 0.3 to the power of 6 minus 4. To be clear, you don't need to write 1 minus 0. You can just straight up write 0.7 to the power of 2 if you'd like. Which is approximately 0.059535, but we'll leave it there. It doesn't specify decimals, so I'm just going to write that many. I mean, and also kind of makes sense. If the probability of getting a goal is 0.3 or 30%, then the probability of getting 4 goals out of 6%, yeah, that sounds about right. Now, this is when we're looking at something called cumulative. Yeah, before we're looking at in our calculator, it will be called binomial PDF, right? I'm going to show you what that looks like right now. In your calculator, if you go to your main screen and you press your interactive distribution / you don't need to focus on inverse, but distribution. Select discrete. And that, because we're doing individual values, you can't have 3.2 of a goal, right? So you're going to discrete, and then finally binomial PDF, because it's binomial probability distribution function. It'll show a little screen, right? It will tell you underneath what each one of these boxes mean. Great. X is the specified trial. So integer from 0 to n. Right, I'm going to put in, what was it, 4. So I want to get 4 goals. Number of trials, how many times am I attempting? 6 times. And finally, a probability of success is 0.3. Hit OK. And there's our answer. So a lot of students will write this in their assessment. Please don't write that. But you should end up with an answer of 0.059535, which is actually the actual answer, not approximate, so I'm going to write equals. Any questions about that? Yes? Sorry, I can't hear you. Yep. Correct, I'm just about to go through that. Yeah, so the one we went through just then was PDF because it's a singular value, right? And this one below it says at least 1 goal. So all of a sudden, it's not, well, let's find the probability of it being 4. We're saying, well, it could be 1, 2, 3, 4, 5, 6. That's where a cumulative comes into play, okay? Now, the first thing I'm going to do is I'm going to show you how to do it without that function, and then we'll go through it, okay? But the first thing I'm going to do is write down that probability of it being at least 1 goal, so x being at least, so greater than or equal to 1, equals to the 1 minus probability of x equal to 0. That makes sense. You see, I'm trying to show you that there are different methods to get to the same answer. And then you would do the same thing and solve, and you end up with 1 minus 60 as your combination, multiplied by 0.3 to the power of 0 times by 1 minus 0.3 to the power of 6 minus 0, which gives you an answer of 0.88231. And this is doable by hand. Yeah, you see how there's a discrepancy between having to apply multiple calculations in decimal form, but barring that last step, right, it's doable by hand. Now let's see how to use that as a cumulative function. So let's say I want to go straight from probability of x being greater than or equal to 1. I go into my interactive, I go distribution again, it's still discrete, but this time I use the CDF. Okay, so binomial CDF. It will give you a slightly different box. I said it will give you a slightly different box. Oh no, that's because I've selected that. Let's try that again. Discrete, binomial CDF. Lovely. So you'll have the only difference being lower and upper. So I'm going to select my values, right? Lower being 1, my upper being 6. My number of trials is 6, and my probability of success is still 0.3. So you see how I'm going from 1 onwards. Or it says, what is it? At least 1. So I'm identifying it's at least 1. It's from 1 onwards. So 1 to 6. Takes it from you. Thank you. You press OK, and it'll give you the same answer. Any questions about that? Okay, let's move on. Probability of 4 times or 4 goals, given that she scores at least 1 goal. I'm going to jump through this quite quickly. So the probability of x being equal to 4, given that x is greater, or equal to 1, which equals to the overlap, so the probability of x being equal to 4 intersecting with x being greater than or equal to 1, over the probability of x being greater than or equal to 1. That's just your conditional probability, which would equal to, because it says the probability of x being equal to 4 intersecting where x is greater than 1, which is just the probability where x equals to 4. I'm going to copy the denominator over. We know the values from earlier, so 0.059535 over 0.882351, which is just 0.0675 in your calculator. Same principles from conditional probability apply. Again, because these are Bernoulli sequences as well, we can assume they're independent. I'm going to pick up the pace a little bit. We have 2 more pages to go through, and it's been 16 minutes, so let's move on. 2 formulas I'd like you to write down. These are very important. NP. Oh, let's try that again. NP, there we go. And NP1 minus P. Okay. So, expected value, we know a formula from prior. This is just another formula. Okay. In this scenario, we have n equals to 45, p equals to 0.4, right? It's just a basic application, non-application question. You just multiply the 2, end up with 18. Done. Move on. Yeah? If your number of tries is 45 and the probability of success is 0.4, you get 18. Easy. The variance in this case, apply the same formula, 10.8, right? But this formula right here is very important. So please make sure you have that down. I will go through this class pad instruction later. Okay, because it's very important in our, that's what I'm looking for, sample size determination. Example 13 says construct and compare the graph of binomial probability distributions for 20 trials with different probabilities of success. Okay. Calculator, what you need to do is go into the statistics aspect of your calculator and just clear it, because you might have some stuff from general maths, whatever it is, but just clear that. We very rarely use it in methods. Once you've done that, in your statistics screen, or your statistics window, there's a calc option, select that, and then distribution. Leave type as distribution, that's fine, but you're going to scroll down and make sure you get binomial PD. Hit next. If you need to, you can select help, and it will tell you what these individual options are, which I think is quite nice, but we'll go to next. And you'll see a screen that looks like this. Anyone stuck on that on the previous screen? Jess, you got it? Okay. X number of trials. I'm just going to select a random value for X, right? That has to be obviously because we're going 20 trials, right? So I'm just going to pick a value of X, let's say 2, right? That doesn't really matter as long as it's within our range. And our probability of success is 0.2. Hit next. And it'll give you the probability. Okay? Are we happy to move on from there? Okay. On the top left is a graph button. Select the graph button and it'll give you your distribution. That's pretty much it. Yeah? It's more of a visual to see where it is. You can use your left and right keys to show what is the probability of getting 3 or 4, etc., right? But that's pretty much all I wanted to do. I'm going to screenshot this and paste this into the document because I want us to compare. Okay, so if I paste it into our document from prior, oh, that's not it. Here we go. There we go. So that's 0.2. Okay, that's 0.2. What I'm going to do now is do the same thing, but I'm going to change the probability of success to 0.5. So let's go back to our application statistics, I'm going to go calculator, distribution, change it from normal distribution to binomial PD, put in a random value of x, let's say 2 again, number of trials is 20, but the probability of success is 0.5. I hit next, I hit the graph button on the very top left of my screen, and we'll have a new one. And you'll notice, of course, that with an increasing probability of success, we end up with differing values of our, differing trends or patterns in our probability distribution. So our probability of success being 0.5 gives us this graph here. And finally, if we do the same thing, I'm going to do this very quickly. Go to statistics again, calculator, distribution, change that to binomial PD, 0.8. I think you get the idea, but I'm just going to quickly do this anyway. 0.8. Hit enter, graph it. You'll end up with a graph that looks like this. So as you increase the probability, right, even the probability of success, even though your number of trials stay the same, of course, you end up with differing expected values. Okay, that's pretty much all I wanted to say. It's generally symmetrical if its probability is 0.5. It's skewed if it's less than or greater than 0.5. That's really it. All you need to know is understand that logic, and also, for example, identify that based on this graph, I should be expecting, for probability of success being 0.2, I should be expecting 1 to 8 successes. That's about it. The probability of contracting influenza this winter is known to be 0.2. Of the 100 employees at a certain business, how many employees would the owner expect to get influenza? Find the standard deviation of the number of employees who will get influenza and calculate the mu minus 2 sigma. So basically, right, what we're applying is that formula we had from ages ago, which is this one at the very bottom, with a probability of a value of x being between mu minus, or say average minus 2 standard deviations, and the average plus 2 standard deviations is 0.95. So that's the same stuff as if you've done the normal distribution from previous years or general maths, same idea. What we're going to do is find our values of mu and our sigma. Our mu, which we know is going to be our expected value, equals to 0.2 times by 100. That is just our number of trials multiplied by our probability, which gives us an answer of 20. Our sigma equals to the square root of our variance, okay, which equals to, and I'm going to use the formula from prior, and we have NP, which is our expected value, so 20, multiply by 1 minus our probability, so 0.8, which gives us an answer of 4. Have I jumped through that too quickly? Okay, that's just the same formulas as prior. Using our calculations, I know that mu plus 2 sigma would equal to 20 plus 2 times our 4, so 28. And I know that mu minus 2 sigma equals to 20 minus 2 times 4, which gives us 12. Now, it says interpret the interval. What does that mean? Right? In this case, the owner knows a probability of approximately 95%. That's 12 to 28 people will contract influenza. That's what that means, right? It should be approximate. Just to be clear, you should never write, it is a 95% chance. It should be approximate 95%. Okay. Any questions about that one? Okay. Finding sample size. Okay. This is the last bit, I promise. While we can never be certain about the outcome of a random experiment, we can identify the number of people, or the number of whatever it is, the sample size required to reach a certain outcome. For example, how many times you need to roll a dice to be reasonably sure of getting a 6, right? Or how many lotto tickets must you buy to be reasonably sure you win a prize? The probability of winning a prize in a game of chance is 0.48. What is the least number of games that must be played to ensure that the probability of winning at least once is more than 0.95? This particular question, A, can be done by hand to a certain degree, but the question B cannot be done with that by hand. So I'll show you how to do the first one by hand. So the probability where x is greater than 1 or equal to 1 needs to be greater than 0.95. Right? That's what the question's saying. Ensure the probability of at least winning once, which will include winning twice, of course. Which would be the same as saying 1 minus the probability of x being equal to 0 is greater than 0.95. Again, I'm showing you different methods. Or, alternatively, right, interpreting that, if I was saying 1 minus the probability of x being 0 is greater than 0.95, I can say that the probability of x being equal to 0 needs to be less than 0.05. Any questions about that? Okay. If you think about it, 0.48, which means that the probability of failure is 0.52 to the power of n, because it's n tries, we don't know how many trials, we just want to write n, it needs to be less than 0.05. And then we're going to use our log on both sides, so ln of 0.52 to the power of n is less than ln of 0.05. I'm going to take the n to the front, right? Hopefully this seems familiar. ln of 0.52 is less than ln of 0.05, and we'll divide both sides by that ln of 0.52. ln of 0.05 over ln of 0.52. Now, should we have a greater than or less than sign? Should be greater than. Why? Because we're dividing, yes, but we're dividing by a negative number, because e to the power of what gives you 0.52 has to be a negative, right? So therefore we have, and by this stage, that's all I'm expecting to do without a calculator. So this ends up being approximately 4.58. 5.8. Now, that's not the question's asking. The question says, what is the least number of games? You can't play 0.58 of a game, so therefore at least 5 games. Even if it said 4.01, it would still be 5, because 4 games does not give you that probability. Okay? So, 5 games. You'd always round up in this scenario. Last question. Almost there. Almost there. I'll give you next lesson to catch up rather than doing new content, by the way. Just give me a heads up. Okay, so what is the least number of games that must be played to ensure that the probability of winning at least twice is more than 0.95? You cannot do this by hand, and I'll show you why you cannot do this by hand. Probability of x being greater than or equal to 2 is greater than 0.95. That's what the question's asking, right? At least twice, so x is greater than or equal to 2. We can do the same thing as before. We can say 1 minus the probability of x being equal to 1 minus the probability of x being equal to 0 is greater than 0.95. That is the same as before. I can use the formula from prior, the binomial one, and say 1 minus n1 minus, times 0.48 to the power of 1 times 0.52 to the power of n minus 1. That is the same formula for x equals to 1. And I think it's pretty obvious that 0.52 to the power of n is no possibilities, or no wins. Needs to be greater than 0.95. How the hell are you meant to simplify this? You can't, right? You have to do it by calculator. Alternatively, we can rewrite it as this. I'm just going to show you an alternate option. As the probability of x being greater than 2 must be less than 0.05. These would be equivalent. But you still end up with the same dilemma, right? So again, back to the calculator. We're going to do that thing I said earlier, right? We're going to go binomial. So distribution, discrete. I'm going to go binomial CDF. Let's go with CDF. Okay, I'm going to start from the very start. We'll go CDF. I'm going to put in, for our lower value, I'm going to put in, what do we want? At least 2, so 2. 2 upper is x, and the number of trials is x, because I don't know what they are. Probability of success is still 0.48. Again, it should give you an error. But you should have binomial CDF 2x, x 0.48. You're going to select that, go into your graph and table. You're going to place that in. But instead of graphing, you're going to press the chocolate bar. When you get the chocolate bar, you'll see something like this, right? To be clear, you might only see, depending on what your settings are, you might only see this. Not this. This. Right? Is anyone having trouble getting to the chocolate bar? Yep. So you've pasted it in. Yep. And you've selected the button at the top. Yeah, I'll show you what I mean. You just haven't. Yeah. I don't know right now, so yeah. Oh, I don't check it out. Do it again. I'll show you what I mean. Alright, so you might be getting some errors, you might be getting a very limited response, but it makes sense if you have, for example, in this scenario, if x equals to 1, if you've got 1 trial, how the hell are you going to have 2 wins? Right? So let's change our, we can, for lack of a better term, call it domain. Select the button on the very right option. Make sure you have the bottom grid or table selected, window selected, and you press this button there. It will show a table input. Start, so what are you starting at? I always just like to keep it at 0. It will say error. That's fine. Ignore it. End. Now, we're going to approximate it, right? So what number are you reasonably certain that you would be able to get 95% chance of getting 2 wins? Well, let's go with, I'm going to put in just 20. I'm fairly certain it'd be under 20. Steps, leave it at 1. That just means you go up by 1, 2, 3, 4, 5, blah, blah, blah. And you should have these options here. Now, what these mean is that here, if you have x equals to 2, so you've got 2 trials, you're expecting a 0.23 chance, or 23% chance of getting at least 2 wins. Okay? Let's keep going down, because the question says we want at least twice is more than 0.95. So the first one that gets to past 0.95 is 8. Any questions about that? Okay, so then you'd write here, well, technically we could solve it, but we're going to go with at least 8 times. Done. Any questions? Okay. I know it's been a very